Hi everyone! This week we are going through the last two parts of game theory. This time we are going to go over sequential games. So what happens if players are not making moves at the same time? And then we will go over the case of repeated games. What if they play the same game several times or infinitely many times? This game could be sequential or simultaneous. First, the usual disclaimer. I do not allow this content to be published without my consent. If I see it posted online, I will take it down and report whoever uploaded it. So, games in matrix or normal form. So, all the games represented by a payoff matrix are said to be in normal form, can only represent situations where people move at the same time. So the sequential nature of decision making is suppressed. We have no way to know who is moving first, and we cannot then analyze such games with a payoff matrix. But many situations involve players choosing actions sequentially over time rather than simultaneously. So we need games in what we call extensive form, and I will show you what extensive form means. So every time you're thinking about sequential game, you'll have to think about extensive form first. I will show you that we can use normal form also one way or another, but extensive form is going to be the most relevant way to represent a sequential game. Let's go back to our number one favorite game, Battle of the Sexes. We are back with Tom and Rosia, who has to decide whether to go to Beaucoup Bakery or to Small Victory Cafe. Two places I highly recommend in Vancouver. Tom prefers to go to Beaucoup as opposed to Small Victory, just because he prefers the bakeries there. Rosia prefers Small Victory to Beaucoup, but anyway, both get positive payoffs as long as they both meet at the same place. If they miss each other, although they might go to the place they prefer, if they miss each other, they get a payoff of 0. So what matters first is that they meet, and then where they meet is going to have an influence on their payoffs. Now imagine that Rosia moves first, and she can let Tom know where she went using a text message or anything else. So Tom is then going to move second after seeing what Rosia decided. So an extensive form game is going to be a game tree. A tree diagram is also called a dendrogram. That's just a fancy word if you want to show off. So, at the top of the tree, we represent the first player. We look at the different options the player has. Here, Rosia can choose between Beaucoup and Small Victory. That opens up two branches, and then it's Tom's turn to play. He himself can go to Beaucoup and Small Victory in each case, wherever Rosia went in the first place. At the end of the day, we end up with 4 different payoffs profiles, which are represented vertically. The first payoff is here the payoff of Rosia. This is how I represented it, because she is first to play. And the second payoff is Tom, because he's second to play. So, if Rosia goes to Beaucoup, and then Tom goes to Beaucoup as well, they both meet at Beaucoup. And according to the payoff matrix we had in the previous slide, Rosia gets a payoff of 1, and Tom gets a payoff of 2. That's Tom's number one option. Not only he meets Rosia, but he meets her at his preferred bakery. If Rosia goes to Beaucoup, but Tom goes to Small Victory, then they miss each other and they both get a payoff of 0. If Rosia goes to small victory and Tom goes to beaucoup, again, they both miss each other and they get a payoff of 0. If Rosia goes to small victory and Tom also goes to small victory, they both meet. This is Rosia's favorite place, so she gets a payoff of 2 and Tom gets a payoff of 1. So a sequential game involves pretty much the same thing as a simultaneous moves game, but some notions have to be refined. A list of players that doesn't change. For each player, a set of actions at each stage. So every time it is their turn to play, we need to report what are the actions that are available. Each player's information at each stage. So one way or another, we need to specify what players know when it is their turn to play. Of course, each player's preferences over all the possible combination of actions. That will give you the payoffs. Now, we also need to be able to list strategies. A strategy, remember, is a contingent plan of actions for each stage or each history of the game. Contingent means that we are considering all possible cases. So what we call, for example, a contingency in real life is a plan B. What if this happens instead? I have a contingency, or I have a plan B. Same thing. Here, the strategy has to specify all the possible contingencies. What if the first player does that? What if the first player does that? What if the first player does this instead? And so on. In this lecture and in this course, we will mostly confine ourselves to sequential games in which players have perfect information. So the history of play at each stage is known. Whenever it is one player's turn to play, he knows everything that was played before. He can observe it. Each player moves only once. That's going to be most of the time, but in tutorials we will go through a case where one player moves twice. So a player moves first, second player moves after that, and then the first player can move a third time. Why not? If you think about a bargaining game, for instance, where you have two players, one makes an offer, the other one can either accept, and this is the end of the game, or reject and make a counter offer. And then it's back to player one, who can accept or make a counter offer. And back and forth, either forever or maybe for a limited amount of time. Strategies are going to be the main thing that are going to change when looking at a sequential game versus a simultaneous move game. So strategy is a complete contingent plan of actions. Here I added the word complete to say that it covers all the possible cases, all the possible histories. So it has to specify what the player does in each possible history. It's not just I go here or I go there. It's I go here if this was done before, I go there if this was done before, and so on. So it's going to make the writing of a strategy way more tedious. And you have to be very careful when writing down a strategy when you're looking at sequential games. Think about the Battle of the Sexes game. Rosia is the first one to move, so nothing happened before her. So she only has two possible strategies. She can go to beaucoup or small victory. For Tom, however, there is a history. So Tom's strategies must include all the actions he would do in each possible history. So instead of just saying he can go to Boku or small victory, that those are actions, a strategy is going to list the actions in each case. So, for instance, Boku if Russia played Boku, small victory if Russia went to small victory. So that covers the two possible actions that Russia can take. If Russia went to 3 places instead, if she could go to 3 places, then Tom's strategy would be go there if she does this, go there if she goes there, and go there if she goes to the 3rd place. So for Tom, writing a strategy is gonna be way longer than for Russia, who plays first. Imagine adding a 3rd player. That would be quite a pain. You would have do this if this guy did this and that guy did that. Do this if the first guy did this and that guy did something else, and so on. In our example, that makes 4 possible strategies for Tom. He can go to Boku regardless. So going to Boku whether Russia went to Boku or small victory before. Then he could also go to Boku if Russia went to Boku. This is why here I put 1 Boku in red. That corresponds to Russia's previous move. And he might decide to go to small victory if Russia went to small victory. So this strategy is a following strategy. Tom goes wherever Russia went. If she went to Boku, he goes to Boku. If she went to small victory, he goes to small victory. Naturally, you have the opposite strategy. The strategy where Tom goes to a different place every time. So he goes to small victory if Russia went to Boku. And he goes to Boku if Russia went to small victory. Finally, the last strategy is to go to small victory regardless of what Russia did before. Why 4 strategies? Because Russia could take 2 different actions, and for each of these actions, Tom can take 2 actions as well. That makes 2 times 2, 4. If Tom could go to 3 places, but Russia only went to 2 places, that would make 2 times 3 equals to 6 different strategies. Now that we have defined the strategies, let's get into finding the Nash equilibria. So if Russia goes to Boku, Tom should go to Boku as well. Why? Because if he goes to the other place, he gets a payoff of 0. And he observes what Russia is doing. So any strategy that involves going to Boku if Russia goes to Boku is going to be a best response for Tom. Right? Tom's best response is to follow Russia wherever she goes. And there are 2 such strategies. The strategy Boku regardless, where Tom goes to Boku no matter what. And the strategy where Tom goes to Boku if Russia went to Boku. And he goes to small victory if Russia went to small victory. In each of these 2 strategies, Tom ends up at Boku when Russia goes to Boku. So these 2 strategies are best responses to Russia going to Boku. Now, we need to do it the other way around. We know Tom's best response to Russia, but we need to know Rosia's best response to Tom. For Rosia, going to Boku is the best response if Tom is going to Boku regardless. If Tom is going to Boku no matter what, Rosia will want to meet him there. But if Tom goes to Boku when Rosia goes to Boku and goes to small victory when Rosia goes to small victory, if this is what Tom is doing, then Rosia doesn't want to go to Boku. In this case, she will be followed, she will be met by Tom no matter what. So, she would rather go to the place that yields a higher payoff. For her, it is going to be small victory. So, she could go to small victory, and in this case, Tom goes as well, and she gets a higher payoff than by going to Boku. So, summarizing these statements, if Rosia goes to Boku, Tom going to Boku regardless is the best response. And if Tom goes to Boku no matter what, Rosia wants to go to Boku. So, the profile of strategies Boku regardless is going to be a Nash equilibrium. We checked best response in both directions. But if Rosia goes to Boku and Tom follows Rosia no matter what, so he goes to Boku when she goes to Boku and he goes to small victory when she goes to small victory, this is not a Nash equilibrium because Tom is playing a best response to Rosia, sure, but Rosia in this case is not playing a best response to Tom because she would rather go to small victory. That's one Nash equilibrium, but we haven't covered all the possible strategies. So let's keep going. We have one so far, and let's look for more. Now, if Rosia goes to small victory, Tom should go to small victory as well, right? He has an incentive to follow her, to get a positive payoff. So any strategy that involves going to small victory when Rosia goes to small victory is the best response. And we have two such strategies. Going to small victory regardless, and following Rosia wherever she goes. Boku if Boku, small victory if small victory. Now let's check the other way around. Should Rosia go to small victory if Tom plays either of these two strategies? Well, if Tom goes to small victory no matter what, Rosia wants to meet him there, right? So, for Rosia, going to small victory is the best response to that strategy. Now, if Tom is going to follow Rosia no matter what, he goes to Boku when she goes to Boku, he goes to small victory when she goes to small victory. Where should she go? Well, she's going to be met by Tom no matter what. So she might as well go to the place she prefers. In this case, it is going to be small victory. Previously, going to Boku was not the best response because she could go to small victory. So, going to small victory is going to be the best response for her. So when Tom plays either of these strategies, Rosia wants to go to small victory. And if she goes to small victory, Tom wants to play either of these two strategies. They will yield the same payoff. So now we have two more Nash equilibria. Rosia goes to small victory in both of these, and Tom in one of them goes to small victory no matter what, and in the other, he just follows her wherever she goes. So, from the previous slide, we have one Nash equilibrium. From this line, we have two Nash equilibria. And since we covered all the possible strategies, we covered the two strategies of Rosia and the four strategies of Tom, then we have all the Nash equilibria for this game. So I see a question in the chat, but I don't understand what you mean. Can you be more explicit or more specific? What do you mean by playing by Rosia? Is a history of Tom. And what do you mean by Rosia already planned the strategy? It doesn't matter whether she planned or not. What matters is at the end of the day, if she plays this, what is the best response? And if she plays that, what is the best response? And the other way around. That's what matters at the end. Now, no need to use uppercase letters in the chat. I can read without them. There are three Nash equilibria here. So, in this slide, we have two Nash equilibria where they are going to meet at small victory. In one of them, she goes and Tom would go no matter what, whatever history. In the other one, she goes to small victory, and this is the strategy of Tom where he would follow her anywhere. Now, why the previous statement is not a Nash equilibrium? Because if Tom goes to beaucoup when she goes to beaucoup, and he goes to small victory when she goes to small victory, so if Tom follows her no matter what, then Rosia prefers to meet him at small victory because small victory gives a higher payoff. So going to beaucoup for her is not the best response in this case. She goes to her preferred option because Tom is going to meet her there, according to his strategy. Cheers.
Sir, can I unmute?
So, any other questions? I would rather not have students unmuted. Usually the sound is bad and there is communication issues. So I would rather just stick to the chat. Remember that for Nash equilibrium, we need to check best responses both ways. Here, Tom is playing a best response to Rosia both times, but in the second case, Rosia is not playing a best response to Tom. So that's why the last profile is not a Nash equilibrium. It turns out that the game can also be analyzed in normal form. But in the normal form, we need to list all the strategies. So now we have to be careful because Tom has 4 strategies. So if I put Tom in rows, Tom has 4 strategies, which I represent with just the first letter of each action. So B means he goes to beaucoup when Rosia goes to beaucoup, and he goes to beaucoup when Rosia goes to small victory. So the first strategy here corresponds to beaucoup regardless. The second strategy corresponds to going to beaucoup when she goes to beaucoup, and going to small victory when she goes to small victory. So the second strategy is the case where Tom follows her no matter where she goes. The third strategy is the opposite. She's avoiding her. He goes to small victory when she goes to beaucoup, and he goes to beaucoup when she goes to small victory. The last one, SS, means small victory regardless. Now, you have to be very careful when writing down the payoffs. First one, if Tom goes to beaucoup no matter what, they will get positive payoffs only when Rosia goes to beaucoup as well, in which case they meet. If Rosia goes to small victory, that corresponds to the case where Tom goes to beaucoup, and so they do not meet and they get a payoff of 0. If Tom follows Rosia no matter where she goes, so beaucoup when she goes to beaucoup and small victory when she goes to small victory, in both cases they meet. In the first case, they meet at beaucoup, which is why Tom gets a payoff of 2 and Rosia a payoff of 1. In the second case, they both meet at small victory, so Tom gets a payoff of 1 and Rosia gets a payoff of 2. In the third case, Tom is missing her both times. He is not going to meet her. So in both cases, they both get a payoff of 0. Finally, if Tom goes to small victory no matter what, in the case where Rosia goes to beaucoup, they miss each other and get 0. And in the case where she goes to small victory, they meet and Tom gets a payoff of 1, Rosia gets a payoff of 2. And you can see that some payoffs are repeating themselves. Due to the fact that we have now 4 strategies, there are 2 different strategies where they meet at the same place. Like these 2 strategies of Tom are strategies where they are going to meet at beaucoup, and so they're going to have the same payoffs. The second strategy and the last strategy of Tom are strategies where they both meet at small victory, and so they both get the small victory payoffs. Now, if you want to find the Nash equilibria, proceed cell by cell. If Rosia goes to beaucoup, Tom can, as long as Tom goes to beaucoup, it's a best response. There are 2 such strategies. That's pretty much the first statement I made in words, but now represented in the normal form. So you can underline 2 and 2, which are higher than 0 and 0. 2 best responses, because they yield the same payoff. If Rosia goes to small victory, Tom wants to meet her there, so there are 2 such strategies. The strategy where he meets her no matter what, and the strategy where he goes to small victory no matter what. Note that the strategy where he always avoids her is never picked as a best response. In fact, it is strictly dominated. Tom doesn't want to play this strategy because he's going to miss Rosia no matter what. Now, let's look at Rosia's best responses. If Tom plays BB, so he goes to beaucoup regardless, well, Rosia should meet him at least. So she's going to meet him at beaucoup, and beaucoup is the best response. 1 is higher than 0. If he plays BS, beaucoup if beaucoup, small victory if small victory, then Rosia can go to beaucoup and she's going to meet him and get a payoff of 1. Or she could go to small victory, she's going to meet him as well and she gets a payoff of 2. She will prefer to go to small victory in this case. Now, if Tom is playing S and B, so small victory if she goes to beaucoup, and beaucoup if she goes to small victory, that's pretty much an avoidance strategy. Then it doesn't matter where Rosia goes because she will not meet Tom. So she gets a payoff of 0 in both cases. Finally, if Tom goes to small victory regardless, then Rosia prefers to meet him at small victory and gets a payoff of 2, as opposed to going to beaucoup, not meet him, and get a payoff of 0. So the procedure is the same. Once you have a normal form, you're good to go. The hard part here is writing down the normal form correctly. Yes, BB is going to beaucoup regardless. So now we can see that again, we have 3 cells where both payoffs are underlined. So we find the exact same 3 Nash equilibria as before. Rosia goes to small vic, Tom goes to small vic no matter what, regardless. Rosia goes to beaucoup, Tom goes to beaucoup regardless. And Rosia goes to small victory, Tom follows her, so he would have gone to beaucoup if she went to beaucoup, but small victory is where she's going to go. Any questions? Is there not a case where Rosia follow Tom? Well, Rosia cannot follow Tom because Rosia plays first. So she goes to a place first. And then it's Tom's turn to play. Now, let's think about this for a minute, because yes, we found the Nash equilibria, but one of them at least is debatable. Think about the first Nash equilibrium where Tom goes to beaucoup no matter what. Well, if he does that, and if he tells Rosia, hey, I'm going to go to beaucoup no matter what, just so you know, then Rosia, yes, will go to beaucoup. But imagine that if Rosia decides to go to small victory instead, does Tom still want to go to beaucoup? So I am debating the best response aspect of the second action. The first action is, if she goes to beaucoup, yes, he wants to meet her at beaucoup. So beaucoup if beaucoup is the first good move. But beaucoup if she goes to small victory is not a good move in the case where she goes to small victory. So imagine that instead of going to beaucoup, she goes to small victory first. Tom does not have an incentive to go to beaucoup anymore. Now he wants to follow her and go to small victory to get a positive payoff. So once she goes to small vic, he doesn't want to go to beaucoup regardless. He wants to follow her. So BS would be a kind of a better best response, if you want. Because they play sequentially, there is a sense in which Rosia can kind of trick Tom by going to small victory first. She's like, yeah, because I know, like she knows, that Tom will follow her. Once Tom gets the text message and he's like, oh, she went to small victory. Well, small victory it is. Right? However, here, this Nash equilibrium suggests that if she had decided to go to small victory, Tom would still go to beaucoup. So you can see how this notion of Nash equilibrium is lacking a bit of a bite. Because once Tom has to decide where to go, well, he's kind of trapped by where Rosia went. Rosia knows that Tom is going to follow her no matter what. So instead of going to beaucoup, she can just go to small victory because he knows that she knows that he will follow her. He will meet her. And small victory is a better option for Rosia. So, out of these 3 Nash equilibria, 2 of them in fact are not that reasonable. I just talked about the beaucoup beaucoup. You can imagine already the other one that is debatable. The third one, the small victory regardless. Because in this case, if she had decided to go to beaucoup, then Tom would regret going to small victory. So we need somehow to refine the idea of a Nash equilibrium. And this is why we are going to talk about subgame perfection. So what is a subgame? It's a very precise definition, so you need to be careful. A subgame is any part of a game that starts with a single node and includes all of the following nodes. So you start at one branch, if you like, one node, but you have to include all the branches that go down. Moreover, if a node of a particular information set is in the subgame, then so are all the other nodes belonging to that information set. Ignore the second part of the definition for now. I will talk about information sets in the second part of the lecture today. For now, we don't need to focus on that. First of all, the definition implies that the game itself is a subgame, because I can start at the first node and include everything else. That fits the definition of a subgame. Now, if players are sophisticated, we should expect them to play a best response in each subgame. So whenever it is their time to play, they will play a best response. And this is what I meant by, if Rosia suddenly decides to go to small victory, then Tom will go to small victory. Whenever this is his turn to play, he gets a text message. His best response is going to be to go to small victory. So somehow, we need our Nash equilibrium to be consistent with this notion that whenever it is somebody's time to play, they are going to maximize their payoff. They are going to play a best response. In this Nash equilibrium, Tom is playing a best response when she goes to beaucoup. But this strategy says that he would go to beaucoup if she went to small victory. Well, in real life, if she goes to small victory, he will follow and go to small victory. So, this strategy is a best response when Rosia goes to beaucoup, not when she goes to small victory. But because the game is sequential, we would like to make sure that whenever it is a player's turn to play, he's going to maximize his payoff. And this is why we need subgames. So, we talked about Nash equilibria so far in pure strategies or mixed strategies. Now, I'm going to introduce a new notion of Nash equilibrium called subgame perfect Nash equilibrium, SPNE or SPE. You might see both in tutorials or exams. A subgame perfect Nash equilibrium is a Nash equilibrium where each player plays a best response in each subgame of the game. So it means that we need to look at the best response in each subgame of the game. So we need to look at all the possible subgames. So a subgame perfect Nash equilibrium is a Nash equilibrium with a property that all players play a best response after each history of the game. As I said, if there is a case where Rosia goes to small victory, then Tom's best response would go to small victory, not beaucoup. So the subgame perfect Nash equilibrium says wherever Rosia could have gone, Tom is playing a best response. In the previous Nash equilibrium, when Tom goes to beaucoup regardless, he's playing a best response only after the history where she went to beaucoup. In the history where she goes to small victory, going to beaucoup is not a best response anymore. So that would be kind of dumb of him to just look at the text and see that she went to small victory and be like, nope, I said I would go to beaucoup regardless, so I'm going to get a 0 payoff. Why? In order to solve for subgame perfect Nash equilibrium, we can use what we call the backward induction method. Start with the smallest subgame at the end of the game. Then you look for the Nash equilibrium in this subgame, and then you move on to the next subgame. Once you're done with the lower subgames, you go to the upper subgames, and so on and so forth. And you go up the tree by highlighting the best responses. Once you find all the best responses, then you can list the strategies that correspond to these best responses. So let's apply this concept to our Battle of the Sexes game. We have 3 subgames here. We have one subgame where, where it is Tom's turn to play. Remember the definition of a subgame? It starts at one node and includes everything under that node. So this itself is a subgame. In this subgame, Tom is alone. He's playing the game alone. If he goes to beaucoup, he gets a payoff of 0. If he goes to small victory, he gets a payoff of 1. What is his best response? Well, here, his best response is to go to small vic. The idea is that in this subgame, we are looking at the history where Rosia went to small victory. So the best response in this case is to go to small victory. Now, let's move on to the second subgame. Here. It's another subgame that corresponds to the history where Rosia went to beaucoup. Tom could go to beaucoup, they both meet, and he gets a payoff of 2. Or he could go to small victory, miss her, and get a payoff of 0. So his best response will be to go to beaucoup. Now, I found the Nash equilibrium in each of these subgames. Even if there is one player, it is still a game or subgame. Now, I have to move to the last subgame, which is the game itself. But I am going to take into account what Tom will do in each case. So Rosia can either go to small victory, and in this case, Tom's best response is to go to small victory. So if she goes to small victory, he goes 2, and she gets a payoff of 2. If she goes to beaucoup, Tom's best response will be to go to beaucoup, and she will get a payoff of 1. So now she has to decide between going to beaucoup and end up at the bottom of the red line and get a payoff of 1, or go to small victory, end up down there and get a payoff of 2. What will she pick? She will pick small victory. Now, we have found the best responses in each subgame. We are ready to list the different strategies. For Rosia, it's easy. She goes to small victory. There is only one branch. For Tom, because there are two branches, we have to specify what is played at each history. So here Tom is going to play Boku if she goes to Boku, and he's going to play small victory if she goes to small victory. The final equilibrium will be small victory for Rosia and Boku small victory for Tom, which corresponds to Boku if she goes to Boku, small victory if she goes to small victory. This is one of the three Nash equilibria we found previously with the normal form game. This is the one where she goes to her preferred option, knowing that, or maybe expecting that he will follow her no matter what. And indeed, that's what he does. In each subgame, he has an incentive to meet her wherever she goes. This is going to be the SPNE. And this is the only one we found. Note that it is one of the three NEs we found before. So, the set of SPNE is a subset of the NE. As in, a subgame perfect Nash equilibrium is a Nash equilibrium. But a Nash equilibrium is not necessarily a subgame perfect Nash equilibrium. The difference between the two is that in the Nash equilibrium, in the Nash equilibria, there are two, which are not SPNE. Tom is not playing a best response in each subgame. He's not playing a best response in each history of the game. So he's rational when she goes he is rational and plays the best response in one case, in one scenario, one history, but not in the other history. Subgame perfect is refining the notion of a Nash equilibrium because it makes players play consistently, in a rational way, consistently in every possible history. Any questions? So in the chat I read, Rosia plays small victory and Tom plays small victory is SPNE. No, SPNE is a profile of strategies. You listed the strategy of Rosia correctly, but you did not list the strategy of Tom correctly. The strategy of Tom is Boku small victory. If you write the Nash equilibrium, the SPNE as you did in the chat, you will not get full marks in an exam, for instance. Now, those are strategies. What will be played is small victory by Rosia and small victory by Tom. So if you say the SPNE is, then you have to list the strategies. But then what you can say is, in the SPNE, they play each small victory. But careful, there's a difference between what the SPNE is and what they play. Let's go over another example. An entry game. A potential entrant chooses whether to enter a market controlled by a monopolist. So imagine we have a monopolist and a firm is thinking, maybe I could get in this market and start making profits. If the entrant enters, then it becomes a duopoly, two firms. Then the monopolist can either, for simplicity, begin a price war or share the market and be relatively nice. So the game is in normal form here, involves only two strategies for the incumbent. The incumbent is the monopolist. Why only two strategies? Because if the entrant does not enter, then the incumbent doesn't have to do anything, doesn't have to change his decision. He's just cruising, stays a monopolist. So let's analyze the payoffs a bit. if the entrant enters and the incumbent shares, so he's being nice to the entrant, they both share the market and they make a payoff of 5 each. It's like collusion, if you like. If the entrant enters but the incumbent fights, the entrant is in for trouble. His payoff, its profits, are going to be -1 because the monopolist is well established and the price war is going to be very hard on the entrant. It's a price war, so the incumbent will also suffer a bit and it will have a lower payoff than by sharing, a payoff of 1. If the entrant does not enter, he doesn't get any profit and the monopolist stays a monopolist, so nothing changes for him. So whether he shares or fight, he doesn't do anything, doesn't matter, he's alone. So his payoff will be 10 no matter what. Let's represent this game in extensive form. Oh, well, first, let's check the Nash equilibria. So if you just do the sell-by-sell inspection, you get 2 Nash equilibria. The entrant enters, and in this case, the incumbent shares. And the incumbent, if the incumbent fights, then the entrant would rather not get in because he would get no profit as opposed to -1. Now, it is reasonable to assume that both of these Nash equilibria are possible if they make these moves simultaneously. However, a game like that, in reality, is going to be sequential. First, we see if the entrant enters the market or not, and then as a consequence, the monopolist will decide to share or fight. So imagine, this is what the game looks like in extensive form. No need to imagine. The entrant can enter or stay out, in which case, if he stays out, 0 profit for him and a profit of 10 for the incumbent. And then if the entrant enters, it is the incumbent's turn to play. He can share, in which case they both make a payoff of 5, or he can fight, in which case the entrant gets a payoff of -1 and the incumbent gets a payoff of 1. We saw previously that the 2 Nash equilibria are enter and share. Enter for the entrant, share for the incumbent. That's 1. And the second one is the incumbent fights and the entrant stays out. Now, if the game is sequential, we still have 2 Nash equilibria. We just looked and best responses are, well, we still have mutual best responses. So we fit the definition of a Nash equilibrium. But if we use backward induction, take a look at that. This will be a subgame. In this subgame, the entrant already has entered, and the incumbent can share or fight. Now that the entrant has entered, the incumbent will prefer to share and get a payoff of 5, as opposed to a fight and get a payoff of 1. So, in this subgame, the best response of the incumbent is to share. In the bigger subgame, given that if the entrant enters, he's going to end up here with a payoff of 5. He has to choose between entering and then sharing to get a payoff of 5, or staying out to get a payoff of 0. The entrant is going to get in. So, the subgame perfect Nash equilibrium will be enter for the entrant and share if enter by the incumbent. Why share if enter? Because here we look at this subgame, and this subgame corresponds to the case where the entrant enters. So we need to specify what history we are looking at. Again, this SPNE is one of the two NEs we found before. But what's more interesting with this one is that it is the best response in each history. Fight cannot be part of an SPNE. No. It is not the best response in this subgame. Fighting is not. Fighting is not. And the idea is that the incumbent cannot commit, cannot tell the entrant, if you get in, I'm going to fight. I'm going to start a price war. Because the entrant could think, ooh, that's a threat. Shoot, maybe I should stay out. But then the entrant can look at the payoff and say, well, once I enter, the incumbent doesn't want to do a price war anymore. So the entrant can impose kind of his decision on the incumbent in spite of the threat. Because the threat is not credible. Once the entrant is in, the incumbent doesn't want to fight anymore. He can only say that before the entrant gets in. Once he's in, let's share. It's better profit to share. So here, the incumbent cannot deter entry. He cannot prevent the entrant from entering. He is stuck. Now, you might have noticed that both of the games we saw, the Battle of the Sexes and the entry game, are both examples of situations where there is what we call a first mover advantage. Here, the entrant has the advantage. In spite of the incumbent saying, I'm going to fight, the entrant is like, no, you're not. You want to get a payoff of 5 instead of 1. So the entrant is going to benefit from that. In the previous game, Tom could say, I'm going to go to Boku no matter what. So he can tell Rosia, go to Boku. And Rosia could say, no, you're not. Because once you're going to know that I am at small victory, you're going to come to small victory. And this way, Rosia can choose her preferred option first. And she has the first mover advantage. Here, the second mover is at a disadvantage. He would like to commit to do a specific action in a specific case, in a specific history, so that it maximizes his payoff. However, the first mover can anticipate that once the first move is done, the second mover is not going to stick to his threat because his payoff is going to be lower. If the second mover had a way to commit, it could be something like having hostage or or some kind of a bond, contract, limiting capacity. If the second mover has a way to credibly threat the first mover, then the first mover will be like, okay, if he's going to do that, then yeah, I should indeed do what he says, pretty much. But the two games we saw today are situations where the first mover has the advantage, sometimes the second mover has the advantage. And in fact, let's go over one such example. Avoiding Sanji. So Sanji likes girls a lot. Any girl, which is why here I just say girl. I didn't give her a name because he would do this for any girl. And he meets a pretty girl and he wants to see her again. But the girl cannot stand him. She wants to avoid him. And now you can imagine how there's going to be either a first mover or a second mover advantage, depending on who, you can imagine there's going to be a second mover advantage. Because one wants to meet the other, but the other wants to avoid the first. So, in this game, they both have the choice to go to party 1 or party 2. If they move simultaneously, then if they both go to party 1, the girl gets a payoff of 5, Sanji gets a way higher payoff, he's happy, he sees her, he gets a payoff of 15. If they both meet at party 2, it's even worse for the girl. Parties could be different. And it's even better for Sanji, who gets a payoff of 20 now. Now, every time they do not meet, so they go to a different party, the girl is the one having a higher payoff, and Sanji is the one having a lower payoff. It's not a payoff of 0, but it is a lower payoff than when he meets her. So if you do cell-by-cell inspection, you will find that the game has no pure strategy Nash equilibria. But as said before, there is at least one Nash equilibrium, so it must be in mixed strategies. I suggest you to do the computations at home and check if they match. The mixed strategies NE here is the girl goes to party 1 with a probability of 75%, and with a probability of 25% goes to party 2. And Sanji with probability 75% goes to party 1, and with probability 25% goes to party 2. In that Nash equilibrium, Sanji and the girl meet with probability 2/3 times 3/4 plus 1/3 times 1/4. Oh yeah, I made a mistake here. One of the two doesn't get 3/4, 3/4, 1/4. One of the two has 2/3, 1/3. I have to correct that. Different probabilities. Anyway, at the end of the day, there is 7 chances out of 12 that they actually meet, either party 1 or party 2. So it's higher, slightly higher than 50% chance that they meet. So what if they play sequentially? And what if the girl moves first? So the girl first chooses to go to party 1 or party 2. And then Sanji gets to learn about it. Maybe he gets a text message from one of his friends at each party. One of them says, she's not at this party, and the other one says, she is at this party, or something like that. Then Sanji has to decide whether to go to party 1 or party 2. And the associated payoffs are here. Now, moves are sequential, so Sanji's strategy is going to depend on each possible history, but since Sanji wants to meet the girl, he can condition his strategy upon what the girl does. And this is where the second mover advantage is coming from. Wherever the girl goes, Sanji can meet her. She wants to avoid him, but he wants to see her, so he will meet her. So let's do the same process as before, backward induction. And let's start with the right subgame here. Well, this is the case where the girl goes to party 2. So Sanji obviously wants to go to party 2. You can recheck with the payoffs. If he goes to party 1, he misses the girl and gets a payoff of 5. If he goes to party 2, he meets the girl and gets a payoff of 20. In this subgame, this is the history where the girl went to party 1. Again, Sanji wants to meet her, so he's going to go to party 1 as well. His payoff will be 15, as opposed to 10 if he goes to party 2 and misses her. Finally, the last subgame, we have to take into account that Sanji will play a Nash equilibrium, a best response, whenever it is his turn. So, the girl can go to party 1, but Sanji will be at party 1, so she will get a payoff of 5. Or she could go to party 2, Sanji will go to party 2 as well, and she will get a payoff of 0. So here, she's stuck. She's going to meet Sanji no matter what. So she's going to choose the party with the highest payoff. And here it's going to be party 1. Again, let's write down the Nash equilibrium. The girl chooses party 1, and Sanji chooses party 1 if she goes to party 1, party 2 if she goes to party 2. In this SPNE, they both end up playing party 1. But the strategy is not just to play party 1 for Sanji. The strategy is to go to whatever party the girl goes to. And since she goes to party 1, he ends up going to party 1 as well. Make sure you can make the distinction between what's going to be played and what are the strategies. The girl is stuck. Sanji cannot be avoided. Now, so we use backward induction to find subgame perfect Nash equilibria. So we use backward induction to find a Nash equilibrium in all the possible situations. Not only the one that is going to actually happen, but all the possible ones, even the ones that will not happen. This right part of the tree will just not happen. But if it had happened, Sanji would have played the best response. Would have played. This is the trick behind subgame perfect. Any subgame says what would happen if. And we want to make sure that it's the best response every time. Now, is backward induction reasonable? So it may work in simple games, like a game like that. You can take a subgame and okay, boom, boom. You can highlight things and go up the tree. Imagine you have more moves or sometimes more players. But imagine 2 players, more moves like chess. How do you do that? How do you make a tree diagram? It's pretty long and painful. You will have to go to every possible ending where you win or you lose, and then you go back up. You say, okay, then I will do this, then I will do that, and so on. I have a question in the chat. Why didn't the girl play P2? Because if she plays P2, Sanji also plays P2, and she ends up with a payoff of 0. Between P1 and a payoff of 5, and P2 and a payoff of 0, she prefers P1 and a payoff of 5. She is going to meet Sanji no matter what. Remember, she plays first. Sanji is going to follow her. But here, between the 2 parties, she's going to meet Sanji at both, but one of them gives her a higher payoff. So she goes to P1. P1 is the best response in this case. It's not great, but it's the best response. Now, it may not always predict actual behavior. Backward induction sometimes cannot predict actual behavior. There could be errors, altruism, fairness, or intention considerations. And I will go through an example in the next slide. Well, in this slide. Imagine the centipede game, because, well, named after the shape of the tree. So we have player A and player B. Player A starts the game. This is this hollow node, and can pass or take, whatever that means. It could be passing a ball or keep the ball. If A keeps the ball, the game ends, and A gets a payoff of 4, B gets a payoff of 2. If A passes, then it's B's turn to make a decision. B can either pass or take. So if he takes, now the payoffs are going to be 2 for A and 8 for B. If he passes, it's back to A. A can take and get a payoff of 16. B would get a payoff of 4. Or he can pass, and now it's back to B for a last round. In the last round, B can take to get a payoff of 32, and A will get a payoff of 8. Or B can pass. In this case, B gets a payoff of 16, and A gets a payoff of 64. Let's use backward induction. This here is going to be the last subgame, the smallest subgame. Right? In this subgame, B can pass the ball and get 16, or take the ball or keep the ball and get 32. He will decide to take the ball because he can get 32 instead of 16. Now, let's go to the second subgame. The second subgame will be here. In this subgame, A can pass, but in this case, B will take, so A will make a payoff of 8. Or A can take and will get a payoff of 16. 16 is higher than 8. So in this subgame, if A gets to play here, he will take and get a payoff of 16. Now, bigger subgame again. B can pass the ball, but then A will take. So B will make a payoff of 4. Or B can take the ball now and make a payoff of 8. He prefers a payoff of 8 to a payoff of 4. So, as soon as he gets the ball, he's gonna take. Finally, the biggest subgame is the game itself. A can pass the ball, but B will take, and so A will make a payoff of 2. Or A can take right now, end the game, and get a payoff of 4. Between 4 and 2, A prefers to take. So, in the subgame perfect Nash equilibrium, A is going to start the game by taking, and that's going to end the game, and B will never get to play. That's what the subgame perfect Nash equilibrium says. Now, real-life experiments on people, students, and so on subjects, has shown that there is some cooperation. So the first player to move doesn't stop the game right away. In fact, there is more cooperation where he passes and then B passes, and sometimes there is a stop somewhere in the middle. Maybe sometimes it stops at the end where they pass all the way. But there is a lot of cases where there is some cooperation in the sense that the first player doesn't end the game right away. So, subgame perfect equilibrium here is not helping us. It doesn't help us predict human behavior in this game in particular, or other games. Note that whoever takes makes a higher payoff. And when the other one takes, it's a higher payoff than when the previous one took. So, when A takes, he makes 4. When B takes, he gets 2. When it's back to A now makes 16. And then if it's B's turn to play for the last time, then A's payoff is lower, it's 8. And symmetrically for B. Now imagine a case where A plays pass first. So I'm not talking about Nash equilibrium anymore. I'm more talking about what's going to be played in the actual game. Imagine that A plays pass first. So here. And remember that both players are aware of these payoffs. They know these payoffs. So now B is like, why did he do this? That's not very rational. Because if now I take, A makes a payoff of 2, although he could have made a payoff of 4 before. So B could imagine a couple of things. And I haven't listed all of them here, but here are some. Maybe A made a mistake. He clicked on the wrong button. Maybe A is altruistic. His utility is actually higher than 2 when the payoff of B is higher. So the actual utility of A is bigger than just what the payoffs show here. The payoffs could be amounts of money. But maybe A is even happier than just getting his money when B also gets more money. So A could be altruistic. Or there could be a third case which is also interesting. Maybe A is actually rational. What he's doing here is he's sending a signal of wanting to go all the way to the end where both payoffs are pretty high. So pretty much he may be implicitly telling B, hey, I didn't take, so you're not going to get a payoff of 2, you're going to get something higher, whatever you do. So don't screw me and let's go all the way to get high payoffs. In this case, B is not using backward induction, rather he is using what we call forward induction. He's thinking about what was played before. Not, when we go backward, we start at the end. And so we are thinking what will be played. When we use forward induction, it's what was played before and what was the meaning behind it. So I know the terms are confusing, so be careful. So B might use forward induction and think, oh, I could take now and end with 8, but if A passed in the first place, maybe he intends to cooperate all the way so that we can maximize our payoffs. And then B could pass. And if B passes as well, then A can interpret this as, ooh, he is playing my game. We are in it together. We are cooperating. We're not even talking to each other. And then he might pass again. Note that at the very end, B here has an incentive to kind of be a dick. Because he says, well, I am going to end the game. So if I take now, I get 32. If I pass, I get 16, but A gets a massive 64. So B could think, well, he was nice to me so far. He didn't make me earn a payoff of 2, so maybe I can go all the way, reward him, and I get still a nice 16. Or he could say, well, I am at the very end. I'm going to be selfish, and I'm going to take and go for 32. Note that A would make a payoff of 8, which is still higher than the first 4. The idea is backward induction doesn't always predict human behavior. Forward induction can be used sometimes to see cooperation where the subgame perfect Nash equilibrium would not predict any. That's it for this lecture on sequential games. Have a good rest of your week, and see you in the next one. Bye.